So what has changed for me since the last time I was here, which was begging a place into this conference as a graduate student? I think Danny received some emails from me in 2016 about that. Is that now I'm working with a large group of scientists, which we are formerly the polar oceanography group at Brown, but now the antipodal polar oceanography group, because we've got people in both hemispheres, and we're quite well distributed. So you'll see a few faces that you remember and several faces in the crowd here today. So thank you for traveling. And we're on 5 continents, but we're missing South America and Antarctica. And like I said, some things have changed, but not a lot. So I was looking at my slides. I'm a masochist, and so I keep every single talk I've given since like 2013, which is terrifying when you go back. But this is the first slide of the talk I gave in 2017. And it was going to be the same first slide of the talk I gave today until I kind of panicked and realized there's like 15 slides that overlap. So the fonts are definitely different now. And I've also indicated, just to show you how little some of my thought process has changed, slides that were on the same one from 5 years ago with this big star. So inspired by not talking about exactly the same things, I'm going to walk through a few things that have gone on in the last couple of years, at least since many of you and I have been in the same room. So talking about problems related to CI sensitivity in the use of large ensembles and in ensembles of ensembles. Something that Letty alluded to in the last slide, which is the observations of waves and ice with new satellite platforms. And then I'll talk about what motivates a lot of the work in my group now, which is how sea ice flows engender ocean variability and how we can parameterize that in global climate model. So we'll start here and talk about the sensitivity problem. Marika spoke a lot on this in the first day of this workshop, but in general, many of you will remember that in the third CMIP, there was a general struggle to reproduce the loss of sea ice. There's the observation, there's the spaghetti models, and it was faster than forecast was, I think, the name of the paper. They seem to do a little bit better in CMIP 5. Observations bracketed, the ensemble of observations bracketed the ensemble of models bracketed the observation. But this was a bit illusory because it was the same problem we've had for decades, which is that sea ice models are inappropriately sensitive to warming. So this is a paper from Erica Rosenblum and Ian, who's here now, looking at how global temperature trends relate to sea ice trends. And generally, the only models that get the sea ice trends right are too warm. This is not necessarily new information. There are papers on this going back into the 80s about how climate models were doing this. So one thing I started looking at was whether we could leverage this massive increase in data, not just increase in data like in the CMIP 5 ensemble, but indeed many models submitted ensembles of data to CMIP 6. And there's also this really great project called the Large Ensemble Project, or CLIVAR Large Ensemble Group. And basically to see if we can explain these issues with sea ice sensitivity, not just in September, but throughout the year, and whether or not there's better benchmarks for us to look at. So I'm using a series of 17 large ensembles to evaluate 2 of these biases that you can find in GCMs. And the first one is internal variability. Letty showed an internal variability ensemble in the last talk. So this just looks like this. Here's global mean temperature from CESM2 in the CESM2 large ensemble, and you can see the spread. And so you form an ensemble mean. That's sort of the force response, and then the variation around that mean is the internal variability, or the simulated internal variability. You can also look at these big ensembles of ensembles. So CMIP 6 had a group of models that submitted ensembles, and there's also the CLIVAR Large Ensemble Project. There's 5 more. So this looks a little bit more like this. This is September sea ice extent from 3 different contributing groups to CMIP 6. Each one of these is an ensemble. So they have an ensemble mean. You can make an ensemble from the ensemble means. That's the ensemble mean ensemble. That has a mean. That's the ensemble mean, and it has a spread. That's the ensemble mean ensemble variance. And that tells you about differences in the overall force response of climate between simulations that's independent of climate or internal climate variability. So if you look at this for one of the classical problems, now we've turned the individual ensemble members on their side. These are boxes, the interquartile ranges here. This is the observation. This is September sea ice area change expressed as a percentage per year, and we can talk about why I choose that in this paper. But what we've noticed from the ensembles is that the CMIP 6 ensemble gets the actual area change, but individual models tend to be on one side or the other. But if you look at sensitivity, so this is September sea ice area sensitivity, they're all undercooked. So they're not warming enough, or they're warming too much if they're getting the right sea ice area trend. That includes the ensemble of ensembles. So those are going to get turned over. And now we're looking at 6 of these. So this is the CMIP6 ensemble, mean ensemble, and these are the 5 contributing members to the Clyvar Large Ensemble Project minus CESM2, because it wasn't available when I produced this plot. This is every month of the year. This is the sea ice sensitivity in each one of those months. And the red boxes mean that the climate model ensemble does not reproduce the observations, which are drawn from a set of, I think, 5 different passive microwave estimations of Arctic sea ice. So that's quite worrying, I suppose. But this goes exactly to what Letty showed last time, which is that there are larger changes in the Arctic than models are predicting. And it doesn't seem like we've done a good job at improving those, even though we might have in September. So these sensitivity biases aren't just a September problem. They're all the time. So one thing that I was looking at when writing this paper was whether or not the marginal ice zone provided an opportunity. So Rebecca Rolfe, I think, was at CPOM, was looking at changes in the marginal ice zone, which is defined by sea ice concentration from passive microwave satellites, and noticed that it actually hadn't really changed its total area. So sea ice is shrinking, the area is staying the same, and so the fraction of the sea ice that's in this low concentration regime, at least as predicted by some of these, or as observed by these passive microwave satellites, is increasing. So it might be possible, because this is sort of the marginal ice zone is something that's not changing, that we can actually examine how model changes are affecting the marginal ice zone, or at least this sort of definition of the marginal ice zone. So they do pretty well, actually. Now I've converted this to a marginal ice zone fraction, so kind of diverging from the Rolfe et al. Paper. But in general, the models seem to do well at predicting both the actual change in marginal ice zone fraction, but they do pretty well in terms of explaining the sensitivity of the marginal ice zone to warming. So what the MIZ, or these low concentration regions in models, are doing are well predicted compared to observations. But I would note there's higher uncertainty both in the observations and in the models. We can make that same plot for marginal ice zone fraction and see a lot of blue. Blue means that your model ensemble is producing the statistically similar distribution of marginal ice zone responses compared to observations. And you'll note some places like this, where this GFDL ensemble seems to not really hit the observation, but we're coloring it blue. So we tested this using a artificially reduced uncertainty in both the marginal ice zone observations and the models, and found basically the same result. So the problem is that there's no problem basically in the winter months, but there is a problem in the freeze-up from October to December, and that presents an opportunity for model evaluation or improvement. So that's the marginal ice zone from passive microwave sensors. And I'm going to tell you about work we've been doing to actually observe the marginal ice zone in a different way using ocean surface waves. So this is a track from the ISAT-2 altimeter. You've heard a few talks that talk about ISAT-2. It's probably the greatest thing that's ever been invented, and I would encourage all of you to use it. It's severely underutilized, at least the sea ice products. So those of us that use them are on the science team related to sea ice. We're like worth $200 million to NASA, because there's like 10 of us using these products, and they've spent like $2 billion. So, you know, there's money for you. They don't give it to me. But so this is an altimetric track. This is from a higher order product called ATL07. So this is the sea ice surface height in an area fully covered by sea ice in the Barents Sea. It's from 2019. And this coincided with the track in this region, so that's east of Svalbard. And this is just before a large storm passed through here in March. This is what a coincident or near coincident track recorded the next day. So this one's going up, this one's coming down. And now you see these high amplitude deviations in the sea ice. These have a characteristic height of maybe 1 meter and characteristic wavelengths of about 1 kilometer, which I'll explain why we see that in a second. But this is surface waves. You can look at this from MODIS. You can look at this from passive microwave. This is 100% sea ice cover. We're at least 100 kilometers into the sea ice. This is high amplitude waves caused by the storm, quite deep into the ice. And something that Mo Mahel, that's his, I think, passport photo. Sorry, Moma, if you're on the call, but has been working on throughout his postdoc is this really remarkable effort to try and not only characterize the spectrum of these ocean waves as they propagate into the ice, but also their direction. So this is probably of interest to a lot of people in this room. So he's gone a bunch further than I did and has looked at the photon cloud. So this is actually a photon cloud of observations of the height of the surface going into the sea ice somewhere in the Southern Ocean. And he can use generalized Fourier transform techniques to actually obtain along track spectra and separate them between wavy variability and ice variability and ocean variability. It's really neat. One thing I alluded to before was that the wavelength of those waves that were observed in that along track measurement were about 1 kilometer. That's not real. Waves don't usually have that kind of wavelength, and that's because the ICET2 altimeter is a straight line measurement that's not aligned with wave crests. So it overestimates the size of waves. So MoMA has also done this amazing work using the fact that there are 3 independent beam pairs that have a coherence. So these beam pairs are going in a straight line. They both sample the surface. They're pretty close to one another. And so the coherent variability between them can tell you both about the direction. These are actually full directional spectra of waves in sea ice obtained from these altimeters. This is the same, these are 3 beam pairs, I think. You can also correct these. So now you have fully corrected directional wave spectra in sea ice everywhere, 14 different tracks a day, so 28 different measurements, I think. It's really cool. And one of the crucial things here that I really like is that MoMA developed this because we were thinking about ice, but this has nothing to do with sea ice. In fact, it's probably an easier problem when you don't have ice. The ice is highly reflective, so you get more samples, but you should be able to get directional spectra everywhere that ICET2 is operating. Pretty neat. So back to a little bit of other work. Because ICET2 measures these waves, we can actually use them to identify areas that are affected by waves year-round. So we've written a few papers on this. I'm just going to show you some aggregate results here. So this is looking at areas where you have a high frequency of waves. This is what we call I think the wave affected fraction. So the fraction of times a modeled cell or a grid cell will have waves in it from these observations over a 3-year period. So this is summer in the Arctic from 2018 to 2021, and this is winter. And what we've noticed, and this could be an issue with ICET2, it could also be an actual physical thing, that there's a much less coherent marginal ice zone in the summer, but not in the winter. In Antarctica, this is largely the same. You can see this thick band of high wave-affected sea ice around the periphery of the Antarctic continent. There's something like this in summer, but it's more diffuse. And this is a 4-year composite now of the marginal ice zone in both hemispheres. This is all-year composite of areas affected by waves in the sea ice from ICET2 altimetry. It's comprised of billions of segments, lots of measurements, and lots of tracks. And you can kind of see what you expect. This semi-wide marginal ice zone in Antarctica. You've got the areas in the North Atlantic and in the Bering that are affected by waves in the north. So this is the place to look at waves. You all know that, but it might also be a place to really think a bit more about these wave attenuation parameterizations. And something we've been focusing on a lot recently is trying to examine the coherence between definitions of the marginal ice zone that are standard, so using passive microwave sensors, which say if you have 15 to 80% sea ice concentration in a region, that's the marginal ice zone, and comparing that to sea ice, the same thing but derived from waves. So this is actually a point of contention in these, let's say, competing groups. So Jill Brewer, her paper was alluded to in the last talk, pointed out that the marginal ice zone, if you saw waves in it, was 8 times wider or 13 times wider, depending on where you were, than the sea ice concentration edge. And I am showing you, this is the waves, this is the concentration, that the waves don't extend deep into the sea ice like the sea ice concentration does. And I think the discrepancy between the two of our results has to do with the fact that ICET2 doesn't always record waves. So there's a lot of instances where you don't see waves, but you do see low sea ice concentration. There's very few instances, I think, where you see low concentration, or you see waves but don't see low concentration sea ice. It's a bit of a biasing of the observations, maybe. So that's a little bit about waves and ice. And this is an old slide. We're now really getting into the old content here. So you've probably seen these photos in some other talks too. Sea ice is a composite material. It's made of floes. We know this. These floes span a wide range of scales, from meters to tens of kilometers, and we use the flow size distribution to describe them. This sea ice geometry, so flow size geometry, for example, is critical for understanding the ocean, and that's the point I'd like to make here. The reason for this is you can see an example of a sea ice edge like you see here. Red sea ice, highly reflective, high albedo. This is like a 90% or 90% reflectivity of sunlight. So you got nothing in terms of a heat flux going into the sea ice, whereas over here in the dark water, it's about 300 watts per meter squared. And so you can build up these immense gradients in temperature and salinity. It's not just solar radiation, it's everything that give rise to ocean variability. An old slide. And you can see that when you actually heat preferentially sides of a domain, this is a general circulation model run at about 50-meter resolution. This is sea ice on the top, and you're just pouring sunlight on top of it. So you get gradients in the surface forcing. That leads to gradients in temperature. Those are what's called geostrophically unstable, and you get this eddy-driven mixing. So the flows, or in this case, the ice edge, is retreating from south to north. Again, an old slide. But we know that there are rectified effects of this, at least in idealized simulations. So when you melt sea ice, the melt rate depends on the geometry of the sea ice. So here's an example with lots of small flows. Here's an example with one big flow, and this is the time it takes, or the total volume curves for a bunch of different GCM experiments as you vary the flow size from effectively 0 to 50 kilometers. So widespread, these are resolved scales in some cases, and the difference between the time it takes to melt might take several months or more. So if you think sea ice flows are important, then you need to understand how big they are, or like what the relevant scale of sea ice flows is for the ocean. And so we've been working with altimetry, so just like ISAT2. Letty also pointed out that we have an immense problem right now, which is that cryosat2 is saying flows are twice as big as ISAT2, or vice versa, I don't remember. But we've been using these altimetric products to try and sample the sea ice surface and recover flow size distributions, or at least moments of the flow size distribution. And the critical problem here is that we have these one-dimensional passes over the surface. This is from cryosat2. You can see the identification of openings and sea ice, but we're trying to recover a two-dimensional statistic, so the area distribution of sea ice flows. I'll skip the math, the statistics we use to obtain these, but just point out that we have a paper from a couple of years ago just looking at cryosat2 and examining the first moment of the flow size distribution, or something like the mean flow size. And this allows us to reconstruct a sort of climatological variability in the mean flow size across the Arctic, and also an annual average. So generally what we saw was that you had this decrease in the typical size of flows through the freeze-up season, and then a constant flow size into the spring, and not much change year to year over time. So the scale here is important. The typical size of sea ice flows, at least sea ice segments, in the Arctic is about 5 kilometers. At least that's sort of the representative radius that's important for the ocean. And that's pretty problematic for us. So this is a flow, beautiful flow. You couldn't tell me how big that is, but somewhere between 10 meters and 10 kilometers. That's the scale of sea ice geometric variation. The eddies that respond to that sea ice geometric variation spin up on time scales less than a day and have length scales of hundreds of meters to kilometers. The size of our GCMs, even these super high resolution GCMs we've been talking about, 2-kilometer GCMs, are not enough to resolve this. They're definitely not enough to resolve the ocean variability, and they're not enough to resolve the flow scale variability, at least in some cases. So this used to appear, actually, on this talk, because that climate models don't actually have a representation of this geometry in them, any variability at any scale. And that's wrong now. We've seen enough talks to tell you that. Some of them do. Some of them have flow size distributions. Many of them are very strongly focused on improving LKFs and fracture features from kilometers to hundreds of kilometers. So there is an effort, strong effort, to include these geometric effects and its potential effects on the ocean. But I'd like to make the case that it's all probably not enough. And the reason is that any continuum model, any non-discrete element model, has to obscure very important processes in the upper ocean. So if we go back to our little happy sun here, it heats the ocean preferentially on one side relative to the sea ice. But an ocean model has a single tendency for temperature or salinity or momentum. And so if you want to force the ocean model, you have to give it a single flux of temperature, salinity, momentum, whatever. That's the average flux by sea ice concentration. That's far too high for the areas underneath sea ice and far too low for the areas under the open water. What this means is there's a process that we've all decided is happening sub-grid scale that we're not really explicitly parametrizing, but that has a resolved effect, as we'll see. So this process is set not by physics, but by the grid scale or the time stepping of your climate model. And it's huge. It has a massive impact, or it has a massive magnitude, let's say. The impact is not quite yet known. to us. The reason this has an impact will take us back a little bit to the standards of QG turbulence. So this is a turbulent cascade. Generally what happens in an ocean model is you have a forcing length scale. This is length scale here, or wave number. You have a forcing length scale, and that length scale is assumed to be disparate from your dissipative length scales. One of them is the rubbing of large scale motions against boundaries. Another one is dissipation at the very small scales, molecular scales. And so because you have this forcing that's different from dissipation, you can have these inertial ranges. There's an inverse energy cascade that takes energy from the forcing scale up, and a forward entropy cascade that takes filaments, basically vorticity, to the smaller scales. In a model, what we do is we create this eddy viscosity that's in the ocean, and that eddy viscosity exists effectively to balance all the production at the forcing scale that's supposed to be dissipated at the subgrid. The problem with sea ice is that you have a multi-scale cascade of forcings. It's not limited just to the atmospheric mesoscales or the synoptic scales. It's every scale, every length scale in between here, because of the LKFs and the fracture features of the sea ice. And this is a problem for trying to infer typical diffusion or dissipative coefficients here, which are based on understandings of this inertial range and subgrid dissipation. What we do that hides this from us is we collapse all of this geometric information to the grid scale, to a binary field concentration, no concentration, or some number between 0 and 1. So that's this subgrid eddy exchange flux I was mentioning just before. So all of this variability and forcing is collapsed here, dissipated instantly. It doesn't impact anything, though it probably should, based on the way that we parameterize diffusion in our climate models. The point is the ocean is doing a lot of work. It doesn't know it's doing a lot of work. It's doing a ton of work. So we can actually calculate the strength of these in terms of fluxes, and they're about 1/3 of the total exchange of heat between the atmosphere and the ocean is being instantaneously mixed at the subgrid. Same thing's true for freshwater forcing or momentum. So it's massive subgrid transfers of energy and momentum, energy and heat, but that are all implied. So we think we have a solution, which is to supplement the existing Smagorinsky type ocean viscosities. So just to back up and just explain where this comes from, this is kind of what I alluded to in that diagram from before. In general, you have these resolved sources of variance production of energy. This is depicted here, integral from 0 to k star, which would be the resolved scales. And that's balanced by resolved diffusion. So this is D is a diffusive parameter of viscosity that's at the grid scale. This is the point. This is how you define these things, and you match them by they're equal. And the magnitude is the energy transfer from resolved to unresolved scales. And this is how you pick D. This is the way that Smagorinsky viscosity is implemented in climate models. In our case, we have to incorporate the effect of subgrid variance production by sea ice, and we could do that in one way by including a sea ice source. So that sea ice source is related to this subgrid variance production, and it gives us an ice eddy type diffusivity. This is the diffusivity that you would apply to an ocean model that's inflated by the fact that you have this concentration-based sea ice model. And we've deployed it. We've put this in NEMO. And if it sounds like I'm building up to something really exciting, I'm not. But I will say this should be important. We can compute the ratio of the sort of unresolved production of variance. This should impact the resolved flow in areas like the Beaufort Sea, and it's small. This is the sea ice part here. It's smaller than the sort of resolved diffusion or the resolved loss of variance, but it's much larger in certain times of the year. But when we include it in NEMO, we've done this in a slab atmosphere, fully coupled ocean simulation, and we see these changes on the margins of the sea ice. But to be honest, I'm not actually even sure what we did. But this is just to say this is very much ongoing. We're trying to deploy this and use this and understand what it could do. You'll notice nothing's happening in the Central Arctic, so we just haven't really looked at these parameterizations in great detail. We think there might be a solution to this problem for continuous sea ice models that don't have LKFs and want to represent the ocean more or better. And this is just a sort of plug. Vero alluded to our work together through the Scale-Aware Sea Ice project. A lot of my group works on topics related to SASIP. And there's a bunch of us as PIs. We're all the co-Is. PI is the contact lead PI. And we're working on building out the next sea ice model and including new parameterizations of ocean ice physics, wave physics, all that kind of stuff. And please come talk to us if you're curious about this. We've got a lot of different people working on a few different things. And that's it. So sea ice is made of flows. We like the MIZ. We can define it with waves instead of concentration, and we've got these issues where we want to reparameterize ocean mixing in the presence of sea ice for global climate models. We got a bunch of websites. That's it. Thank you. While we do questions, I'm going to show you videos from various people in the group because I didn't talk about them at all. This is Anna and Sam. They're both here over here, and they've been working on this discrete element model that Veronique alluded to yesterday. This is really cool. Ocean eddies and bringing flows and things. Here's the Southern Ocean from Nexim. We just did the first integration with Nexim. Rafa and Guillaume are working on this. Cool. Go ahead, Vern.
In the first third of your talk, the first part, like you showed the variable, like the seasonal variability, like of the sensitivity to warming.
Yep.
And the CAN-ESM on the lower left there, like seemed to have a very good one. And I was wondering, is it because it's too thin, or is there something that we can learn from this model that?
Yeah, that's a good question. I didn't think too much about the specific models themselves. It was more of to prove a point that the marginal ice zone fraction was a useful metric, but not to actually go into the details of what each individual modeling center was producing. And I think because Marika showed this on Tuesday, that like CSM2 seems to do better, but I didn't have access to CSM2 when I was producing that paper. So, you know, it might be that, you know, improvements in models are actually driving improvements in that metric.
Are there any other questions? Yes, I see one hand.
About the sea ice diffusivity you introduced, is it like a purely lateral thing, or it does also affect the vertical?
Yeah, so it's not
fluxes?
It's not parameterized as a vertical diffusivity. It's only a lateral one, so it'll be viscosity and diffusivity.
If there would be vertical component to it, and it would
there
have
definitely
much more impact than lateral.
Your point is well taken, but the thing we know we can diagnose is differences in horizontal variance. So we're thinking about the variance of inappropriately characterized variance at the subgrid scale, and that's horizontal variance. It's the same for vertical variance, and maybe we should think about how to incorporate that as well. Lisa has a question.
So follow-up question, the NEMO lack of or your disappointment with NEMO results, is there any issue with resolution there in terms of, would it make a difference if you go from, I don't know, 50 kilometer to 5 kilometer resolution horizontally?
Yeah, it's a good question. Certainly, we think that this kind of doesn't matter, at least in terms of whether or not this sort of application should apply. It's not really resolution dependent in the way that CS concentration is simulated in models, but I wonder, we haven't really thought about it. Basically, we have colleagues in France who spared us a little bit of time and said they'd chuck some numbers into some parameterization in NEMO, and this is what we got. So it's not at the stage where we're really assessing it, but certainly being here has helped me.
I'm thinking about that at the coarser resolution grid size, you have much more smoothing, so this impact might be less visible.
Yeah, I think you're probably right.
Could you say a bit more about the differences with the Brewer et al. Study on the ISAT2 waves?
Yeah. So Jill's paper was really cool, and she went a lot further than our original paper, me and Ed's paper. Get there someday. But so the difference between our two approaches was that Jill basically went through and she looked at every single track that ISAT2 had that intersected with the Southern Ocean, which is a tremendous amount of work, and then went to each one and calculated, basically did Fourier transforms of the along track wave spectra and calculated the width or the distance those tracks went in. So when they reported the results, they reported the difference between the places where they observed waves propagating in the ice and how far the sea ice concentration dropped to below 80%. So there's a bit of a bias in one of our results because obviously, if you only focus on the places where there's waves, the waves will go further than the sea ice concentration contour. But in my case, I said if there were no waves, then I didn't calculate that. And so we're probably underestimating the width of the MIZ. And I think she's right. So when you have an energetic wave event, it's going much deeper than sea ice concentration would exist, but you don't have energetic wave events all the time.
Trying to get me fit, aren't you?
Sorry, Adam, you had a question? Adam, you had a question? I'll repeat it out loud. No, go for it. Bruno's already asked
I
a
don't
question.
understand this figure because like just year-to-year variability, the ice edge will like the MIZ is moving in and now depending on year-to-year and seasonal would be even worse. So I would have expected to see some blue everywhere, but I only see it in one location.
Yeah, so this is a bit tricky. It's a composite, and it's looking at if you take a single cell here, you've got 48 months or 60 months or something like that. How frequently would we define that as the MIZ in these observations? And so there's plenty of places where these are on the periphery. They're only there one time or twice, and so they're 100% MIZ. And there's places closer to the interior that might only be recorded as a MIZ once or twice in 5 years. And so it's more of a schematic than it is actually a like emblematic of where. Sort of think of this as some, yeah, that's what the MIZ would be like if you drew it in your dreams.
Okay.
One last question, and then we'll move on to the next speaker.
Sorry, I ran over.
At the other end again. I'll come round. Question.
Yeah, I was just wondering about the parameterization for the effective diffusivity. Sorry, I got that wrong. Yeah, so obviously you've what the motivation behind that parameterization was, because if I understand correctly, it's in terms of concentration, and that's not necessarily going to, I guess, capture the full kind of variability you might expect from different flow geometries across the scales cover. So I just kind of what the motivation behind that was and the impact that like approximation would have, if my understanding is correct.
Yeah, so one of the problems that Taylor and I have been working on this for like 3 years. This was like kind of the whole point of my postdoc when I started. Is that we're not even really sure which direction it should go for the existing parameterizations, whether it should increase mixing or decrease mixing. So that's probably a main zero-order problem to have. But the general motivation was that, yeah, you have this cascade of different length scales that's injecting energy into the system, and they're smoothed out by the models necessarily. Even the models that have LKFs still have a concentration that they're simulating inside the interior of LKFs. They might go binary, they might have ones and zeros, but in general, it makes it tricky to know. And you can diagnose the amount of subgrid mixing that has to be occurring. And it's much larger in a lot of cases than is meant to be occurring in the model. So, yeah.
Okay, can we have the next speaker come forward and thank Chris again for what is a very interesting presentation.